Hello, everybody. Welcome to today's current seminar. Today we have two speakers, two types. Our first speaker is Haoyang Zheng. He will be giving a talk on ultra-fast language generation via discrete diffusion divergence instruct. Haoyang Zheng is a PhD candidate in the School of Mechanical Engineering at Purdue University, advised by Dr. Guan Lin. He studied generative modeling and reinforcement learning from a probabilistic modeling perspective. His research interests include large language models, continuous and discrete diffusion models, reinforcement learning, sampling, and optimization methods aimed at improving latency and robustness. With that short introduction, the floor is yours and you can start your presentation.
Okay, thanks for the kind introduction and thanks for the invitation from Professor Kanya Dekis. And it is my pleasure to give a talk at Crunch Seminar. And today I will give a talk of our recent work on large language models. And the title is here. And we also call it DiDi Instruct. And this work is a joint effort with a fantastic team of collaborators like Xin Yang from UT Austin, and Cindy is a PhD student at Purdue, and Nan was graduated from Purdue University and now is a tenure track assistant professor, and Julian from AUS. And unfortunately, I did not get his photo for this slide, but since he is worked closely with Professor Kanya Dekis, I believe many of you are familiar with him. And Wei is another Purdue alumni who is now a research scientist at Morgan Stanley. Also, Wei Jian graduated from Peking University and is currently a research scientist at Red Note. And also Dr. Guang Lin. So I will start with my talk with a brief introduction of diffusion language model, how it is different from auto-regressive models, and why do we care about diffusion language model. And then I will give a mathematical definition. How do we define the forward and reverse process of diffusion language model? How to define the objective to train diffusion language models? And then will be the main part of this talk, the proposed DiDi Instruct, which can distill a student model to do few-step generation or faster inference. And there are four main challenges in this work, and when we developed this method, and I will talk about how do we address them. We also develop a lot of experiments to validate our method, which we'll introduce in the experimental section. And the last part is our future plans. I would briefly introduce some directions that we are developing related to DiDi Instruct. In nowadays, I believe all of us are familiar with a large language model, especially the auto-regressive model, just like ChatGPT or Gemini. They generate sequence token by token from left to right. And it works well because many companies do a lot of infrastructure to optimize them, but it still faces a major limitation of the inference speed. Thinking about the thinking mode in ChatGPT or Gemini, they need to generate a vast amount of internal tokens to reason a problem before giving an answer. So for complex tests, we often have to wait minutes to get a result. And due to this bottleneck, there's a growing trend in academia to explore diffusion language model as a potential solution. So the core feature of diffusion language models is parallel sampling. So in each step, the neural network will predict all the logits for all tokens simultaneously. So theoretically, this means we could generate a complete response in just a single sampling step. But we also need care about the generation quality. So doing it in one step is quite difficult in practice to get a high-level, high-quality text. So a common trade-off is to generate 2 tokens per step. which can achieves achieves quality compared to autoregressive models. And that means without considering any infrastructure optimization, uh, diffusion language model can achieve like 2 times speed up compared to autoregressive model. But clearly, this does not reach the theoretical speed limit of diffusion model since they can generate everything at once. So to bridge this gap, we propose DiDi Instruct, and it allows like up to sample 64 tokens in a single step way while maintaining high quality. And without any infrastructure optimization, this means it achieves like 64 times speed up compared to autoregressive model. And this is the motivation that we develop DiDi Instruct. And there are some other interesting statements that motivate in this area. And for example, there are some informal argument says that when human process language or understand language, we do not necessarily read from left to right token by token. We just try to capture some keywords to understand the information globally. And another point is that if we consider some multimodal tasks like image generation, video generation, they inherently do not have a natural left to right order. So sampling from a random position, just like diffusion model, these are much more reasonable, like to forcing them in an auto-regressive order. So this means diffusion language model might be more compatible to do multimodal tasks than autoregressive model. Okay, so before I dive into the mathematical formulation, I actually create like some animation to help you understand how diffusion language model works. Like what is the it is similar to continuous diffusion language model. It has forward process and reverse process. And for the forward process, at first there's a complete sequence, clean sequence, and at each step, we randomly select a subset of tokens, just like this red one and this red one, and then we for the forward process we transform them to mask token, just like this one, and then we fix these two tokens. And then for the next step, we transform the other two positions from the test to a mask token. And then we keep doing this. And finally, what we got here at the end of the forward process, uh, you get a complete sequence of mask tokens just like this one. And this complete the forward process. And for the backward process, we need to define a neural network. And in practice, we randomly select certain mask positions, just like this red one. And based on the network's output, we sample the token and convert the mask token to text. And once these tokens are sampled, they are fixed, and we continue. And we for the next step, we sample the other mask token and transform them to a text. And we keep doing this until finally, for the backward process, we recover the whole sequence, just like this one. And I hope this help you understand the process. Yeah, and yeah, if you have any question, just feel free to stop me, and I will try my best to explain everything. Okay, all right. So that okay, we already have a high level understanding how the forward process and the reverse process look like. And here's a mathematical definition. And just like the continuous diffusion, we have time step t, and also we have a complete sequence of data x. And different from the key difference here, different from the continuous diffusion is that we also need a corruption rate because we need a rate to say that we transform the token to a mask state. Yeah. After define this, we also continue to define the transition probability. So we need to define a transition from t equals to 0 to an intermediate state zt. And we also need to define another transition probability from from time step t to the time step s. Yeah, so I think that's all we need to define the forward process, or maybe we also call it absorbing process.
Hi. I
Um,
have a
Hi.
question. Um,
yes, please.
yeah, just a quick question. In the last slide, I just wanted to ask, the corruption rates are always non-negative. Is that correct?
Yeah. It should be between 0 and 1. Yeah.
Right. Okay.
Yeah, thanks for the question.
Well,
Any other
I have
question?
also, yes, I have one question. So how do you define this transition matrix there? Like, in the end, are you wanna try to learn them, or is like you define them from beforehand?
Yeah. How do that's a good question. So yeah, for the backward process, we need to approximate this forward process to like learn how does it uh get the transition probability. Does that answer your question, or if you have some
Can you say that again?
anything? Sorry, can you say your question again?
Can you explain again how do you define the transition probabilities if they're learnable? I didn't. Sorry, my internet like got, so I didn't hear what your answer.
Do you mean how do I define the forward for the transition probability?
Yes. How do you construct them? Like,
Construct them. Uh, yeah. So I think you first need to have the corruption rate. So you first need to have a time step, and the time step correspond to corruption rate. And once you have the corruption rate, you can use this equation to say for this if we have a intermediate step t, uh, you use this equation to like calculate the probability at this state, how it start from the data to the intermediate state zt.
oh,
And
okay,
then for
okay,
yeah,
but
and
then it means, yeah. So then I mean it will be associated with the way that, because here it says that every time you randomly replace some tokens, you mask some tokens, right? So
yeah, yeah, that's right.
if I understood correctly, what you said is like you actually compute the transition probability. That's what, if I understood what you just said. And if you compute it was based on the two
Compute.
states, right?
Yeah, you can. Yeah, I think you can see that. We just follow this equation to compute the probability.
Okay.
Yeah. Does it make sense?
Yeah.
Yeah. And this is categorical distribution if you're not familiar with. Okay.
Thank you.
Yeah. Yeah. Okay. Yeah. So later we'll move on for the reward process. So we need to first parameterize the neural network, and the input is the token ID times the time, and the output is the logits. And we also need to define a transition kernel, just like to approximate the forward transition kernel queue. And here, I actually have an example to help you understand how this neural network neural network works. So if we consider a batch size 8 and the sequence length of 1000, and also if we consider a tokenizer, a tokenization like ChatGPT, which would ChatGPT-2, which would be 50,000. So the input of the neural network would be the batch size times the sequence length, and we would input the token ID here, so it will be an integer. The dimension is 1, and also we need to input the time step, and then we output. For the output, it has the same the batch size and sequence length are the same, but it also but the difference here is that now it output all the logits of the possible tokens, so it will be 50,000. And with these logits, we can transform them into probability, and then we sample just like autoregressive model to sample the token with logits. And the difference between the continuous diffusion is here because for the discrete diffusion, you need to sample the token. That is a discrete operation. So here we need to use the corruption rate that we defined previously. So with probability 1 minus alpha t, we keep the current position remain mask, and with probability alpha t, we will transform the mask token to a token, and we will sample that token according to the logits. And here's an example. So suppose the corruption rate would be 0.1 at this time. That means because we have the sequence length 1000, that means around 100 positions will transform from the mask token to the text. Okay, that's how we define the reverse process. We need a neural network and also a sampling and also a sampler to sample the token according to the logits that's provided by the neural network. Okay, so now let's look at how we actually train the neural network. So this is similar to continuous diffusion. So we train this with negative evidence lower bound, just like this one. Okay, so I think at this point we can train the diffusion language model, but there's a still obvious bottleneck here, which why we care about distillation. So the issue is that while the elbow trained model generate high quality text, it does not fully unlock the potential for ultra fast parallel sampling. Like to maintain a high quality generation, we are forced the diffusion language model to like sample at most 2 tokens for each step. That means for the diffusion language model trained by the elbow, it still requires like hundreds or even thousands of function evaluations, and that leads to substantial latency. So to get a faster inference, we propose DiDi Instruct. The main idea is that we define a student model, and the student model have the same input and output of the teacher model. The teacher model is a diffusion language model trained by the elbow, and the main difference between the student and teacher is that the student can do few step generation, and it requires like 8 steps or 16 steps to generate the high quality test, just like the teacher model. That means improve the speed up compared to the teacher model. And the theoretical foundation is distribution metric distillation. So we define the integral KL-divergence, and we train the student model so that it can do the few step generation. Okay, so Actually, this distillation works well in continuous diffusion, and I will first briefly introduce how it works in continuous diffusion, and then we will explain why it does not work in diffusion language model, and then how we solve some challenge to develop this framework. So for the continuous diffusion, if we want to do distillation, we also need to define a student model, and the input, output, and the network structure is the same as the teacher model. And we also need to define the forward marginal for the teacher model. You have the neural network P theta to output the logics, and then you get the data, and this Q is of some forward marginal, so it will corrupt to some intermediate state ZS. And this is how we define the forward marginal. And our objective is to have the integral KL-divergence to match the distribution between the student and teacher, just like this one. The main challenge here is that the QV and Q theta here, we cannot get them when we train the neural network, and I will explain this later, but you can remember this at this time. So to get a tractable objective function in this work, which we call Diffusion Instruct, which is published in Europe's 2023, it actually developed an objective like this one. So I will give some high-level intuition of this objective. So SV and F theta is a score of the student and the teacher, and the partial dt, partial theta is the gradient with respect to the data. Is the data is a gradient of the parameter space with respect to the data. So that means it can be written as a product of the score difference and the data with gradient of the data with respect to the parameter space. And for this one, we can get the sample data, and then we use AutoGrad to calculate this one. And for this one, the score of the student and teacher we can directly get them. So that means this objective is totally tractable, and we can directly use this to distill the student model and do the few step generation. And this is good in continuous diffusion, but when we apply it in the diffusion language model, we actually encounter some issue. And the main issue is this term. As I mentioned before, this partial dt, partial theta, it use AutoGrad to calculate the gradient, but this one is actually not because in diffusion language model it involves some non-differentiable operation like argmax. We need when we use the logics to sample the token, so this one will interrupt the computational graph, and this is why in diffusion language model this objective does not work. Okay, so let me stop for a while if you have any question.
Maybe I have a question. It's like it's general about distillation.
Mhm.
In this case, it means that your model would perform it, and then after its training will be just as good as the teacher model. So it cannot outperform the teacher model, or it is a way after, like, to do something to improve it further.
Actually, we have when we do the distillation, we have to match the performance of the teacher model. If you look at this red line, this is our proposed method, and this is a matrix to test the performance of diffusion language model. The smaller, the better. So when we do the distillation and when we have the fast inference, we require to at least match the performance of the teacher model. So the teacher model is a blue line. That means if we like consider 16 steps, the sample quality can match the teacher model. And if you just use 8 steps, it does not match. So actually, we would select 16 steps to do the inference. Does that make sense?
Yeah, so it actually can outperform it. And one question here, how did you choose that teacher model? Why, I mean, is it possible to choose like something like, I don't know, like Gemini 3.0 or something that is a bit more like, that is,
Yeah, that's a good question. So I think for our framework, the function for teacher model, there will be 2 functions for the teacher model. The first is to have a good initialization for the student model. So for what you said, Gemini, if you use autoregressive model, I think the network structure are different from the diffusion language model, so we cannot directly use it for initialization. And another way we use this is because we need some regularization when we distill the model, because uh, it is an abrupt improvement. So sometimes it will the objective will like force the student model too much, and it will lead some performance issue like model collapse. So we need student model to like to let the student know you cannot move too far away from the teacher model. So this is a regularization. And yeah, so I would say if you use autoregressive model as teacher, it does not work. You still need to like train a teacher model with elbow, or maybe you just use some open source diffusion language model as a teacher. Yeah, I hope this answers your question.
yeah, that makes a lot of sense. Thank you.
Mm-hmm.
Hi, I
Okay.
had one clarification on what has been discussed so far. So, is the
Mm-hmm.
teacher model being also trained in this process, or is it frozen throughout when the student is being learned, when the student model is being learned?
Yeah, that's a good question, which I will explain later, actually. So for the teacher model, we will the parameter will be frozen. It's just like a reference for the student model. We do
Okay.
not train the teacher.
Okay. So initially you have like a fully properly trained teacher model, and now that is being used to train the student model. Is that how it works? Or is the teacher model also
Yeah,
updated
it's
during the update of the student model, like during some intervals?
the teacher model is just like a good initialization for the student model. The teacher model will not be trained during the distillation. It is just frozen there.
Okay, got it. And also, could you
Does
like
that make sense?
elaborate?
Okay.
Also, could you elaborate on the difference in the inference process? So now, when you are having the autoregressive models, you respect the causality there,
Mm-hmm.
right? Because you're having masking only for the
Mm-hmm.
future time steps. But in this case, are you saying that the masks are randomly generated and then you're trying to reconstruct the words from that? Is that how it works?
Yeah, that's right.
Okay.
Yeah. Actually, for some, this is a naive setting. If because we mainly focus on distillation to do fast inference, and of course there are some advanced decoding strategy to guide you how for diffusion language model how you can get a better sample quality. But because our work mainly focus on distillation, so we just use the naive setting, just like we randomly decoding each position. Yeah, that's a good question.
Got it. Okay. And also, is this
Yeah.
some way similar to BERT,
Mhm.
like some scheduling of the BERT models? Because even in BERT, you have these maskings which are done like randomly, right? With some fraction defined.
Yeah, I believe diffusion language model. So there are different types of diffusion language models. So because like you see here, our we mainly focus on mass diffusion model. So yeah, it actually get a lot of idea from BERT, like to have different noise level to handle different noise levels, and we also like scale up BERT. Yeah. I
Okay.
hope that answers your
Yeah,
question.
thank you.
Mhm. Yeah. So if there's no other question, I will move on to introduce our training framework. So as I mentioned before, we have the teacher model and the student model. The teacher is frozen, and we only train the student model. And because we also consider some adversarial training, so we also consider a discriminator here. And the main process is here. We first have the sequence of mask tokens, and we input them to a student model and teacher model, and we require them to recover the whole sequence and then corrupt to some random time step ti, and then we get the partially masked sampled sequence, and then we input them to the discriminator. So the task for the discriminator will be identify the sample sequence, whether it is from the student or whether it is from the teacher. And then we have the ground truth and the binary output of the discriminator, and then we have the objective to train the discriminator. And on the other hand, we also input the student sequence to the discriminator, and the discriminator will do some transformation, and we have some reward signal. The reward signal will be used to train the student model, and we train the student model and the discriminator alternatively. And finally, when we trained well the student model and the discriminator, the student model can do the few step generation, and the discriminator can classify the sampled sequence from the student and teacher. Okay, so let's try to tackle the first challenge that I mentioned before in continuous diffusion, that the objective cannot be used in diffusion language model. So here we first have the some mathematical theorem, mathematical derivation to get this score function identity. So we get some idea from the policy gradient, and we decompose the integral KL-divergence to the product of the reverse signal times the policy gradient. And the reverse signal here is the log density ratio between the student model and the teacher. And it actually like to tell you how much you should update along this direction, along this parameter space. And the gradient term is just like the tell you the direction that you should update for the parameter space. So with this policy gradient form objective, this can be directly used in training the diffusion language model. And I also want to give some high-level idea why this objective is effective, and why this can allow student model to do few step generation. And if you look at this diagram, it is actually visualize the reverse process, and we start at time t equals to 1, which is a fully masked sequence, and for the final destination here, t equals to 0, this is the fully unmasked fully unmasked and a clean sample here. And for the teacher model, it trained with the elbow, so intuitively, this objective aligns the update direction at any given point with the tangent of the trajectory. Okay, so that means if we have many backward steps, and we can set the step size to be pretty small, so the discretization error here remains low, and we can have the teacher model to get a high quality test. And however, if we force the teacher model to do some like few step generation, and the step size here will be pretty large, and this introduce a large approximation error. That's why the teacher model cannot do well in few step generation. Okay, so for the student model, our objective changes the update direction. So it forces update direction at every point on the trajectory, point directly to the final destination at t equal to 0. Because of this, even with the step size is pretty large, the student can still move in the correct global direction. That's the fundamental reason why the student model is capable of few step generation. Okay, so this is how we address the first challenge, and the second challenge is that the objective here is not tractable. Just like I mentioned before, it is because the log density ratio, this QV and the Q theta, is not tractable. It is the sum of the product of this. You first have the neural network to output the sample, and then you have the forward process to corrupt it to some intermediate state Q at time s. And this requires to go through the whole discrete space to get all the x. So this is not trainable. And our solution is that we refer to GAN to have a discriminator. So we have the discriminator which have the same input of the teacher model, and we have the binary output for the discriminator. So when it trained well, it can represent the log density ratio between the student and the teacher, just like this one. And then we can represent the reward as a function of the discriminator, just like this one. Okay, so here's another challenge is the training instability, and this is inherent in the policy gradient. It is because while it uses unbiased estimation, but it introduces high variance. And what we would see when we train the diffusion language model is that it can somewhat generate high quality sample, but the sample diversity is bad, so it may cause some mode collapse issue. And to address this, we actually consider two different strategies, and one for the reward part, and one for the gradient part. And for the reward, we get some idea from GRP. We get some idea from DeepSeek to have GRPO. So we first have a batch of reward data, and then we calculate the mean and the variance of the reward, and then we directly normalize the reward signal, just like this one. And to stabilize the gradient, we actually decompose this term into two terms, just like this one. And here is a visualization of how do we do this decomposition. So this is still a backward process, start from t equals to 1 and ends on t equals to 0. So for the left term, it's just like this blue line here is start from t equals to 1 and directly points to t equal to 0. And this would work well if we just use one step during the inference. But diffusion language model is a pretty complex, challenging task. So we would say we cannot just use one step to get a high quality sample. So normally we will require, in our experiment, it requires like 16 steps. So that means if we train with this blue line, it does not encounter any intermediate state in the trajectory. So when we do the inference, when we jump to some intermediate state here, the student model does not encounter the situation in the intermediate state, so it will fail and it will have some mode collapse issue. And when we have the right-hand side, when we decompose it into two terms, it's just like this red line here. So normally we would first sample the time step Ti, and then it corresponding to intermediate state Zi. So we would start from T equals to 1 and then point to the intermediate state Zi. And then we start from Zi and point directly to T equals to 0. And this actually addressed the mode collapse issue when we train the student model. Okay. So the last challenge here is that actually we have trained the discriminator, and the problem is that can we leverage the discriminator to help the inference? So the high level idea is that because the discriminator can use some reward signal, and if we follow the reward signal, it will guide the inference to some high reward region, and this actually helps to get a high quality sample. So what we did here is that when we do the inference, we get the discriminator and transform them to the reverse signal, and we inject the reverse signal to the sampling step, just like this one and this one. And this actually improves the sample quality a bit. Yeah. So these are the 4 challenges that we face during when we propose this distillation method. And for the remaining part, I would like to briefly introduce the experimental part. So for a quick review of the setup, we conduct our experiments on OpenWebText. And for the model, we have the teacher model and student model, which have the same 169 million parameters. This is a pretty small model. And for the discriminator, because we replace the output from the for the teacher model, it outputs all the logics, and for the discriminator, we just require it to be a binary. So for the discriminator, we initialize from the teacher model, and then we replace the feature head. So it will be 131 million parameters, smaller than the teacher model. And we consider H100 and use a DAMW to train the neural network. And yeah, so this is the main results that we got, just like what we show here before. So this blue line is the teacher model, and the red line is the model distilled by the DiDi Instruct. And the green line and orange line here are some other distillation methods, just like consistency. They based on trajectory-based the distillation. So it is clear that our method performs always the best across different number of sampling steps. And the perplexity is the matrix, like I mentioned before, the smaller the better.
I have a question. First, can you give us an intuition of what does the perplexity measures? Like, how is it? How? Yeah, I understand lower the better, but what it is? What is the thing that is measuring? That's the first.
Okay, that's a good question. So, perplexity is like you have a reference. So the reference is advanced auto-regressive model, and uh, when we calculate perplexity, we do something like cross entropy. So we compare so from left to right, we compare each token compared to the advanced large language model to compare whether they are the same and different. If they are the same, that means it get a good performance. If they are the different, the perplexity will increase. So it's just like we require this student model to generate a sequence of tokens, and we compare it to an advanced large language model to compare whether they have the same quality. Does that make sense?
Kind of, but in this case, when we're talking about language, that there are many possibilities. For example, there would be many ways of answering a question that may be valid, right? Like, so in that case, like doing a comparison one word by word wouldn't a bit misleading.
Yeah, that's a good point. So I would say that we actually will perplexity sound like a very naive way to detect the performance, and there are some other metrics that may be a good alternative compared to perplexity. So actually, if we want to detect whether it performs good, we for the formal way, we need to do some downstream task, like we test in uh, we first have the backbone, and then we train some like feature head, and we test whether this backbone can have a good sample quality to maintain the sample quality, something like that. So I would say perplexity is a very simple way, but I think it is still a good indicator to say that our distill method achieves good performance. Yeah.
I see. That makes sense. Thank you for explaining.
Mhm.
Yeah, it makes sense. And also, maybe I have another question here. Like, if I understood correctly, when you had like this plot of the trajectory, and you said that the teacher model will go tangent to the trajectory, but your model will somehow cut it, like do some kind of shortcuts, right? And, but if the blue line, let's say, if it will get you to the endpoint of the trajectory, and in the end, the red one also would get you to the endpoint of the trajectory, why can you achieve better performance with the red one if the endpoint of the trajectory is the same?
Okay. I see. This is a good point. So actually, when we train, if we go back to the framework, actually we replace this teacher model to a data. So actually, when we train the model, we use some data as a reference. So that's why it can beat the teacher model. Does it make sense?
Yeah, that makes a lot of sense. Okay, yeah, great, thank you.
Yeah. So yeah, I think yeah, there are some misleading here. Yeah, probably. Actually, when we train the model, the teacher model, when we have the reverse process, is pretty slow. So uh, actually, we would replace it with the data, and we corrupt it. So that makes the training much more faster. Yeah, this is a good point.
Thank you.
Okay. Yeah, so later we also did a lot of ablation studies to test different component of our DiDi Instruct framework, because like I mentioned before, we introduced a lot of component like GRPO, score decomposition, and this reward guidance. So we need to test each component, whether it works well. So for table 1, we start from a baseline without any tricks. Without any tricks like GRPO, score decomposition, and we test the performance from 8 steps to 128 steps. And then later, we for each row, we add one technique that we mentioned before. And finally, for the last row here, we add all the techniques that we mentioned before, and this is the performance that we get. And you would say from table 1, that actually each component contribute to a better performance of diffusion language model. And for the table 2, this is another ablation. So we start from the last line here. This is the baseline. So for this one, it is got the same result of the last row here. So we have all the tricks here. What we did here is that we remove one tricks, but keep all the other tricks here. So you would say the performance, we also test all the performance from 8 steps to 128 steps. Okay, so later we also do some model scaling up because nowadays for large language models, maybe most people are interested in whether it can scale up. How do we scale it up? So we also did a little bit scale up to have 400 million parameters. And we also test perplexity and entropy. So perplexity, the smaller the better, the entropy, the larger the better. So the red line here is the results that when we scale up. So you will see when we scale it up, it actually performs better. And we also did some, we also have some other applications like protein sequence generation. And yeah, I think it is because DiDi Instruct is not specific to diffusion language model. Actually, it can be applied to discrete diffusion. So there's a general part of the diffusion models. So that's why we apply it in different applications like protein sequence generation. And due to the time limit, I will skip the details here. But in general, it actually performs good when we apply to different applications.
Hi,
Yeah.
sorry, I
So
have a question.
mhm,
I just
yeah.
wanted to ask, do you know what protein this is?
Sorry, because I'm not responsible for this experiment, so I'm not quite sure. I just know this is done by the second author, so he used the model from the TikTok, and
I see.
they
Um,
have, yeah, they have.
Also, like another question I
Yeah,
just wanted
please.
to ask is like, how do you make sure that it is preserving the certain function constraints that are there in a protein structure?
We
To validate whether it
yeah,
is
that's a good.
accurate or not. Yeah.
This is a good question. So I think we have some metrics to validate the details of the like how do we how do the protein maintain some constraints. Because like I mentioned, I am not
Yeah.
responsible for this experiment. You may need to go into the paper to see. And I
Okay.
believe, yeah, they did some work to validate that.
Okay.
Yeah.
Perfect.
Thanks
Thank you
for the
so much.
question. Mhm. Yeah. So the last part is that there are some future promising directions that we are exploring at this time. The first is like I mentioned before, the diffusion language model are compatible with image and video, and we are doing some text to image, text to video generation. And we are also interested in scaling it up, like to scale up to 7 billion diffusion language model, like LiDAR. So I think the main challenge here is some infrastructure issue. Is because previously when we have like small model like 169 million parameters, we can when we distill the model, we can use data parallel distributed data parallel to train the model, and one GPU can have all the entire model. But if we scale it up to 7 billion, I believe one GPU cannot have such a large model, so we need to do some tensor decomposition or state decomposition. So that's all the infrastructure optimization that in this project that challenge us. Another promising direction is called block diffusion. It is because nowadays autoregressive model have a very good infrastructure optimization, and we want to leverage the advantage of both autoregressive model and diffusion language model. So that's why block diffusion gets popular nowadays. So the main idea is that we decompose this 1,000 sequence to some blocks, like 32 blocks, and each block got 32 tokens. So we start from the first block, which is the first token to the 32nd token, and within this block we use diffusion to generate the token. And once it's complete, we move to the next block, the 33 tokens to the 64 tokens, and we also use diffusion to generate all the tokens, and then we move to the next block, and so on. And the good thing is that once we complete the first block, the second block can use the KV cache that we have in the first block. And this can actually get good inference speed when we use block diffusion. And if we consider DiDi Instruct here, actually we can allow autoregressive model to generate 32 tokens at one step. So that means 32 times speed up compared to autoregressive model. Yeah. And I think that's all I want to share today. Yeah, thanks for listening, and I'm happy to answer any question.
Thank you so much for your great talk. So now we open the floor for questions. Do we have any other questions for a speaker?
Yes.
Yes, Jen.
Hi. I'm a postdoc. My name is
Mhm.
Zheng. So I
Hello.
try to hi. Well, I try to understand the big picture. So here, basically, a teacher model is given, and by using the technique like the distillation, you can reduce the number of the the inference model inference. So that's the key idea
Yeah,
here.
that's right.
So from like 1,000 to
Yeah,
like
that's right.
16.
Yeah. Just like this figure. Yeah, the red one here. We want to have a fast inference.
Oh,
Yeah.
okay. So if the number of the function evaluation is like 16 from the beginning, it is fully random. So you need 16 steps to get the final sequence. Is that the right way to interrupt?
Yeah, I think so. I would say like we have fixed the sequence length like 1024, and if we have autoregressive model, because you have to sample token by token, so it requires 1024 number of function evaluations to complete the sample process. And for mass diffusion, if every time we sample
I
2
see.
tokens, so that means it requires 512 NFEs to have the sample. And if we have this like 64 times speed up, it requires like 16 NFEs to
Yeah.
generate the sequence. Yeah.
Yeah, got it. Thank you.
Thank you. Thanks for the question.
Do we have any other questions?
Haoyang,
Or
this
do you want
is
to-
very good. Can you give us a feel of the time cost, like for the smallest model to 400 million parameters to what you're targeting now on H100? What is it? A 1 day training? Is it 1 week? What is it?
Oh, it is because, yeah, that's a good question. So because it is actually a very small model, like 169 million parameters. So actually, it just takes one GPU hour to complete the task.
Oh, 1 GPU. I didn't see that. Really, 1 GPU. So when you go to
Yeah,
400, when you go to 400 million parameters, how does the scaling go? Is it linear? Is it quadratic? Should be transformers,
Actually,
right?
I remember it takes like 2 hours, probably 2 or 3 hours. It does not take too much. Like for example, for the previous for the consistency model, I believe to get this performance, they require like at least 20 or 30 hours. Yeah, the training is pretty fast for our DiDi Instruct method.
So it was 30 hours and it goes down to 1 hour.
Yeah, that's right.
So you said you have a 64 speed up, right? 64 times speed up. From
That's
from
right.
the worst case, yeah.
Yeah, I believe the reason they require so many hours is that they do something like a progressive training. So they start from a very small step to match the teacher model, and then they gradually increase the step. So that means it like takes like 6 or 7 rounds to train the model. So that 6 to 7 rounds require a lot of time. Yeah.
And how about the protein generation that the example that you show? How long does that take?
Sorry, I do not ask the second author, so I believe it is also pretty fast, because like I remember it takes like 2 weeks or 3 weeks to complete the test. So I would say maybe 1 or 2 hours to complete the distillation. I do not have the exact number, sorry.
But here, because I did ask you about the constraints, here says protein unconditional generation. Does that mean that unconditional means that you don't really obey any constraints?
Yeah, that's right. Yeah, there's no prompt or anything. Yeah.
All right, thanks. Great talk. Thank you.
Thanks for the question.
Yeah.
Thank you, Professor
Thank you.
Kaniadakis.
Yeah. Do we have any other questions? Because I want to close this session. Thank you so much for your great talk. And now it's time
Thanks
to
for your
move on to
time.
our And now it's time to move on to our second speaker. Steven, can you hear me? Our second speaker is Steven Masala. He will be giving a talk on hybrid twinning using PBDW and DeepONet for the effective state estimation and prediction on partially known systems. He was born and raised in Congo, Brazzaville, where he completed most of his education before moving to France to pursue his undergrad and graduate studies. He is currently a final year PhD candidate in a joint program between École Normale Superior Paris and Nanyang Technological University NTU Singapore, working on the Descartes project, which aims to develop digital twin technologies to support decision making in urban context. With that short introduction, the floor is yours, and you can start your presentation.
Thank you, Naz.
Yep.
Yeah, so she already presented. I'm actually third year PhD, but in France we usually do short PhDs, so it's my final, and I'm going to defend my PhD in 2 months actually. This research is actually based on some work that I did on my first year PhD, and I'm trying to make it as short as possible. Naz, is there any constraint on the time? Can I make it shorter?
Yes, you are like the second speaker and last speaker, so take your
Okay.
time. And it usually goes for 1 hour, but you can present for like 45 minutes, then we have
Okay.
question and answer session.
Okay. I actually made it so that it goes quite fast. I standardize it, but so anyone can stop me at any time to ask question. You can feel free to do so. So the context of my research and my PhD is about this program called Descartes, and it's a collaboration between France and Singapore. They aimed to create a digital twin for urban context. So they want to have this twin that will allow them to help them make decision in complex system and in real time with a lot of uncertainty and things that we don't know a lot. So most of the use cases in the project are related to energy, drone trajectory, and remote sensing. So there is a lot of structural health monitoring, drone trajectory planning, where you update the trajectory of the drone in real time, and some energy grid update model. So in this project presentation, I'm showing one algorithm one project that we did for the first year of my PhD, but that was also applying in a drone case later, and so I will show it at the end. So hybrid twin, in the way that we define it, is this additive model combination between a physics-based estimation and a data-driven correction, where you have a physics-based model. Okay, you can see. Can you see the mouse moving?
Not really.
Oh, okay. Okay. So you have a physics-based model that makes estimation and a data-driven model that correct based on experimental data. That's the idea of an hybrid twin. And this data-driven model can be a machine learning model where you can learn the correction and correct. The idea is to have it in real time and make a prediction and correction approach on system like that. In the context of this research, we have an environment that we don't know perfectly. Like we might have a wind that is changing, or some assumption that we made on the physics that is not correct, and we will try to make the best modeling approach to take into account this uncertainty. So the idea at the end is to have this hybrid twin where you can control it, and then you can apply it on dynamical systems as well. That's changing. Yeah, so the construction of the hybrid twin is, as I said, this additive approach. It usually comes with a lot of challenges. For example, when you are combining the two elements, the physics-based approach and the data-driven correction, you want some complementarity. You don't want to have a data-driven correction that is adding information that the physics already has. So this orthogonality or complementarity is what occurred the most when I started this PhD, and I really wanted to work on that. How do you actually work on that, and how do you ensure that what you are correcting is complementing what exists. And the idea is to have it in a control loop later so that you can have a model that is getting better and better over time as you are controlling it. Yeah, so the combined model layer is the hybrid twin. The one that we built in this research is based on the idea of the PBDW. So this approach, which is called parameterized background data weak, we inherit from that and then we build on top of it because this approach is very interesting. It was built by Yvan Madej and Anthony Patera and all in 2015. This is a data assimilation task where they try to reconstruct the state of a system, U, here, as an additive combination of physics-based estimation and data-driven correction. So in the same spirit of the hybrid twin that I just introduced earlier. And the originality here is that in their formulation, they managed to have a naturally orthogonal combination in the way it's built. So here the eta, which is red here, and z live in two spaces that are orthogonal. So that allows you to correct and enrich the space of the physics-based estimate, which is blue. So we wanted to actually build on top of this because of the mathematical property of the approach, which gives you a good view on the convergence of the error estimate. It also comes with a built-in a priori error estimation, which is also that we can quantify thanks to the F-sub stability constant here, the beta. And it comes with a way to select the sensor that maximize the enrichment of the space. So it's a very interesting approach, and it was extended to time-dependent problem by Willy Haïk and Ludovic Chamois in 2023. So which was the PhD thesis right before me. They extended it in real time to deal with biases that changes and how do you correct them in real time. So this is what I will be building on top of. Please, you can stop me at any time if you have a question or if you want me to clarify anything. So here we will build two spaces. We work with two spaces. The blue spaces, which is the background space, is going to be the physics-based estimate, and then a red space, which is going to be the observation space. The observation space is going to be spanned by rich representer of experimental data. So we will assume here that we have a lot of experimental data and we have a incomplete physics-based model. So it's a physics model that does not represent completely the reality. We might have made a lot of assumptions or we don't understand the physics properly. So just estimating the state with that physics-based model would give a wrong estimate. And correcting them with the experimental data it would give a good estimate, and putting more experimental data would give better and better estimate. So that's the idea. And there is a way to actually deal with noise because even though the physics is wrong, the experimental data might be noisy. So in the optimization problem that they solve to find z and eta here, there is a way to tune the hyperparameter of the regularization to balance the trust between the incomplete physics and the noisy data by following a kind of Mozorov discrepancy approach.
Stephen,
So
can you say something about the two spaces?
Yes. So the first spaces is the physics-based space here is built with a reduced order model. So we use the reduced basis approach. So you can, let's say you solve your model many times and then you have this parametric domain. You choose the parameter, you solve the model for different value of that parameter that cover your parametric space.
What is it? Is it a Hilbert space? Is it Banach space? Is it H1? What is it?
Here,
or subspace of that.
Yes. So here U is let's say the physics-based space, you can approximate it with finite element. So the solution, the space in which you define your solution is going to be the same space as you are building the physics-based space.
So for example, H1.
For example, H1, yeah.
All right. And then the data space?
The data space, so you will have, I actually have the next slide, for example, here. You have the physics space on the left, which are the different modes, first mode, second mode, third mode, fourth mode. And the second observation space are Ritz representer of the experimental data. So you have the first sensor, for example. Here we model the sensor as Gaussians. You have the first sensor, the second sensor, the third sensor, and observation space is the span of those Ritz representer. So that would basically tell you where you need to correct the information, for example. So those two spaces are the two spaces that we will use in this presentation.
But so is there noise in the data, or you don't assume any noise?
Sorry?
The data are noisy, so on the observation space, because you can have stochasticity. How does that come in?
Yes, so we assume that the sensors are noisy. So that's why in the optimization we have a regularization, the XI. In the second line, implementation online, if you can see the argInf.
So uncorrelated noise.
Yes.
Okay.
Yes. And then in the saddle point, so the solution of this problem reduced to this linear solution, the saddle point problem, where you can see that the solution, the first line and the second line, if you look at the second line, the projection of eta on B gives 0, and in B you have all the physics mode. So that tells you that there's an orthogonality between the data-driven correction and physics-based space with every single mode of them. And the Y is the experimental data. So we fix the experimental data as a force, we force it, and then we find the physics estimate and the correction that such that the sum of them gives the experimental data.
Okay. Thank you.
And yeah, here the quality of the estimate actually it is dependent on the stability constant, the F constant here, the beta. So the better the beta, the bigger the beta, close to 1, the better we have the better estimate we have. So in the way we choose the sensor, we also use the F constant to choose the next sensor that maximizes the information gain from the correction. And so we follow this algorithm that was built by, I don't remember who exactly, but it was in 2015 in the same paper as Madej, that rely on this greedy stability approximation, where you maximize the stability and you minimize the approximation error at every time you choose a new sensor, and that allows you to better correct and cover the physical space. So I will just give an example of solving a PDE with the PBDW that I just presented, which is not what I built, but we are building on top of
So
that.
I have a question on that. So if you don't move the sensors, if you don't do adaptive sampling using this greedy method, then you cannot guarantee that the spaces will be orthogonal.
The space is going to be orthogonal no matter the choice of the sensor. So it's by construction here in the saddle point construction.
Right. The saddle point gives you the orthogonality.
Yes. But the question is interesting because if we choose them well, then we need less sensor. And we actually have a unique solution if a better condition on the unicity and the existence.
Okay.
By
If
doing
beta
so.
is very small, let's say 0.01, that's bad. So you have to do adaptive sampling to improve it. Yeah.
Exactly. Yes. Yes. If beta is very bad, we need more sensor to improve the beta.
Yeah.
And if it's good, then we did less sensor. But the condition here to have at least existence of the solution is we need at least as much sensor as physics mode. So here the physics space is a reduced order space, and we use N mode and M sensor. By using this algorithm, we can use N sensor, and it will work. But if it's not optimal, then we might need M bigger than N to have existence at least. And the idea would be that if we have less sensor, then we don't have enough sensor to understand the physics mode. So the physics mode are less and less observable, and we might have instability in the idea. So the numerical example to just show it, so here I just chose one example, which is the Helmholtz equation, which is actually the initial problem that they chose in the paper. So you have this domain, the physical domain is this square domain, and then you have the Helmholtz equation, and then we have a bias. So the bias here is introduced because we are making the assumption that the physics is imperfect. We don't know the physics perfectly, and here the bias come in the source. So the source here is Q in the second right hand of the equation, and then in that source we introduce a bias G, and that bias is going to represent our lack of understanding of the physics. And then the dot red are some of the experimental data. We also introduce another bias, the bias in the boundary condition. So let's say the reality is that those boundary conditions are based on Dirichlet conditions. But when you are solving it, you don't know, and then you solve it with Neumann. So that's also a misconception of reality. So we have different biases. This is the problem that I will solve with AI later. But in this experiment, I'm just showing the perfect example without bias. So those are the two spaces. So for example, for a perfect model without bias, this is how the PBDW works. So you have the physics-based estimate on A. So this is the estimate by the reduced order model. And then you have the correction by PBDW, which is based on the observation data. And then the sum of them give you on C, which is the estimate of the state using this hybrid approach. And then you have the relative error with the finite element approximation of the same state on D. And then we do that by increasing the number of modes, and then we see how this approximation change. So we fix the number of sensor to 50. So we have 50 sensor and then 2 POD mode. And then by increasing the number of POD mode, we will see that the error is getting more and more local. And we actually need more sensor, and the error increasing where we are far from sensor. So if you look at the yellow is the error is big, and red is the error is low. If you look at the yellow areas, most of the yellow areas are between sensors. So this is what I was talking about, instability as well. By increasing the number of modes for a fixed number of sensor, we get unstable. But if here we add sensors, it would be better, especially in the yellow areas. So that's actually one of the criteria that is used in the sensor selection, in the stability, maximization, and approximation error minimization. Okay, so now I will introduce the contribution that we had during my first year of the PhD. So the idea is now to say we have a model, the physics-based model. We will not replace the physics-based model with an AI approach in this context. We will instead replace the data-driven correction model with an AI approach. But the condition is that we want to learn only what we don't know. So we will try to force the AI approach to live in the orthogonal complement of the physics-based space so that we can correct efficiently. So here the new problem is this hybrid twin is going to be physics-based estimate plus AI correction. and AI correction is going to be a DeepONet. DeepONet, why? Because I went to the PINS summer school in 2022 in Stockholm, and that's where I was very curious about DeepONet, and I learned it there. And I remember I was asking a lot of questions to Raj and George about this orthogonality. And I spent most of my time after that to working on this problem. So here the idea is it's interesting. DeepONet was interesting in this case because in DeepONet you have two AI model that you are projecting on each other, and the second model is actually different vectors, and you learn them as the same time as you're learning the coefficients. In this case, since we know the space in which we want to live, which is the space of the ignorance, we can replace the trunk with a set of bases that we can build by ourselves. So that was the idea in here. How to learn something that you don't know is to build a set of vectors that are orthogonal to what you know and force your AI to live inside. You have two ways to do it. The first way is the physics informed. You could actually penalize the orthogonality to the physics-based estimation. Or you could simply do a physics constraint approach where you just replace the trunk with a set of bases, which is what I'm showing here. But in the paper, that if you want, you should be able to find it with the title, using the title of my presentation. In the paper, I discuss both the approaches. So here I'm just discussing the physics constraint because it showed better performances. So the idea here is to say the bias eta that we built here, in red, we can see that it's a linear combination of coefficient and vectors. Here the vector is actually a Ritz representer. And then the coefficient is how much do you put weight on that. The Ritz representer are built, constructed offline, so we don't need to relearn them. So the DeepONet here is only learning the coefficient, and then the output is projected on the Ritz representation. So what we do is to say that if the output of the DeepONet is a combination of those coefficients on the physics-based mode, on the orthogonal complement of the physics-based mode, it means that the projection of the bias is always going to be orthogonal to the physics estimate. And that's how we construct it. And by construction, we have a constraint that is existing all the time, compared to a physics informed orthogonality, where you would have something that's working by average. Here you have a constraint that's working all the time. So you are training with the constraint, inference, you have the constraint, and it's working all the time. That was very important for us to guarantee that so that we correct efficiently. And then in the loss is just the classical MSE loss. And the training data was different value of the data. So we would solve the PBDW many times. We have different value of that data-driven correction. And then we train the AI on minimizing the L2 distance with those data. Yeah, so the classical DeepONet is actually on the left. And then the contribution of this paper is on the right, where we replace the trunk with a set of bases that we build, and then the output is projected on the Ritz representers to reconstruct the scalar field of the correction. And then when we sum both of them, we get the estimate with a guarantee on orthogonality. Yeah, so that's the approach in this paper that I wanted to share here. In terms of advantages, why is it more interesting, or what does it bring compared to the PBDW? It's just that instead of solving the saddle point problem with this complexity on M and N, we can solve on the reduced order space only, and then the AI would make an approximation. So the inference time goes almost to zero. It goes very, very low, especially for system where we have a lot of data. That would bring a lot of that would bring the computational time very low, and that's interesting. And I just wanted to also say that all this is possible because this saddle point problem can be decomposed into two problems, one constraint problem and one linear problem. And the linear problem is easy to solve. The constraint problem is easy to solve as well. So instead of solving the saddle point problem, my approach is reducing into a two-step where we do the inference on the eta, and then we solve the constraint problem using the inference on the AI. So the problem is actually equivalent. And then we actually tried it on some cases. So still on the Helmholtz equation, here with the bias is on the boundary condition. So instead of having a Dirichlet, we used the Neumann, and the prediction of the bias using the approaches on A. The correct bias is on B. The physics-based estimate is on C. And then on D, you have the hybrid twin using this DeepONet approach and the orthogonality. On E, you have the PBDW without DeepONet. And then on F, you have the ground truth using linear shape function, polynomial function using FEM. So in this case, I didn't use a ton of data to train this. I used, I think, maybe only 1,000 couple of data to train this, and it's already showed quite interesting result. It could learn that we are wrong on the boundary condition. You can see that the value is different on the border. And in terms of error, we were around 7% on the error, like the L2 error on the field, compared to 5% of the classical PBDW. So PBDW did better. This DeepONet and PBDW did faster and 2% worse in this case. And then in this case, it was a combination of boundary condition and source. So wrong source and then wrong boundary condition. The prediction of the DeepONet plus PBDW is on A. The prediction of the bias using DeepONet. The true bias using PBDW is on B. And you can see that the DeepONet with the strong orthogonality managed to get this source and boundary condition error with slightly some mistake on the left corner. And so on D, you have the hybrid twin using PBDW and DeepONet. E is the classical PBDW, and F is the ground truth using FEM. So in terms of error here, we were super close to the PBDW. I think it was 2% and 4% compared to the ground truth FEM. This work was extended to time-dependent problems. So I also worked on an encoder-decoder approach to do the same thing without DeepONet. And then it was also extended to time-dependent using a transformer to see if we can learn some encoding. And then it was applied. So what I've been working on recently is to apply it on a drone. The idea is, let's say you have a drone and then you have a change of environment. So how do you actually update your model using the real-time information? So we also applied the PBDW on this. So the idea was to do a Bayesian model updating. So the idea is to say, in this case, we have inertia that's changing. For example, one of the motor is going to break at some point, or maybe it's hurt something, and the inertia changes. And how do you actually then now we have a bias on the inertia because you didn't model the inertia perfectly. So the idea is to say, okay, we can use this dual Kalman filter where you have a filter that's tracking the parameters, and then the observation is actually the PBDW. So instead of having a fully data observation on the Kalman filter, we have a physics hybrid physics and data that is correcting the bias, and then we update the parameter in real time. We tried it on this case. For example, in this curve, the curve on the right is how is the bias estimate in real time, and how the bias contribute to the state estimate of the drone in a 25-second simulation, for example. And here the case was, let's say you have your drone going on, following a trajectory that is fixed from point A to point B, and then half the way at 10 seconds, the inertia suddenly dropped. And how do you adapt to it super quickly to regenerate like the trajectory that you can still follow using an MPC? So that's one of the cases that where we use this PBDW into the observation of a Kalman filter to correct it. So you can see that the three components of the inertia were updated quite fast to allow the MPC, the control to be done on the trajectory that we defined. Yes, that's one of the use cases that I wanted to show, the L mods and this one. And then in terms of computational time, using this without PBDW on the drone would take a little bit longer. PBDW would gain few seconds or millisecond on the control because you're solving an optimization problem at every time step. Yes, that's it. That was my contribution for today. I would love to take any question or contribution. Yes.
Yeah, thank you so much. Do we have any questions for the speaker? I can see only George
Maybe I have a question.
and Juan. Yeah. Go
Hi,
ahead,
Stephen. That
Juan.
was a really good presentation. Thank you so much for sharing with us.
Thank you. Thank you,
And
Zheng.
one of the things that you were mentioning was like, did you choose this way of imposing the throne because you wanted to put orthogonality, right? And then you said that there are two ways of doing it. One was like with this physics-based approach, which you have like a self-constraint. And but there's also like another one. I'm not sure if you compared it, like when you do some kind of QR decomposition or SPT, like DeepONet, and they also essentially what they're trying to do is to transform your basis to make it orthogonal. Did you compare with that framework to see? Oh,
No, I've never heard of that. Can you say more? The orthogonal to what?
yeah.
So no, it's not what he wants. So this is orthogonal. The base is orthogonal itself, but it doesn't guarantee that it's orthogonal to the physics modes. So that's a
Oh,
different.
okay. Oh,
It
okay,
could
okay,
be
okay.
fast. It could be different. So that's his. It doesn't really care about the trunk basis because he replaced the trunk basis.
Yes.
That's the
Yeah, so you replace with the trunk basis as is orthogonal in the physics, right? So they are not orthogonal between themselves.
They are because I built them with a kind of Gram-Schmidt autonomization.
Okay.
And I build them sequentially one by one. So I ensure that they are each of them in orthogonal to what I want, so the physics that we already know, and then they are also orthogonal to each other.
Okay. Okay, understand.
But I will check the QR that you mentioned too. I will read the paper. Thank you for sharing.
so this is called the two-stage two-stage training of pins.
Okay.
Yeah, the author is Shin, Shin, a former postdoc here.
Okay.
But why the accuracy when you use the DeepONet? Why is it worse?
Oh, because I didn't use a lot of GPUs. I think I just did 1,000 simulations. And then I tried it on a very simple case and it was already amazing. So I didn't, I was like,
Oh, okay. But
yes.
there's fundamentally, there's no reason that it would be worse, the accuracy, right?
Yes. Yes, it should match.
And
It should match.
in terms of computation complexity, if M equals N, I think the factor, the speed up factor is 8/3. I check 3 plus 3 in the middle, 6 plus 1 plus 1, 2, 8. So that's 8n cubed versus 2n cubed.
Okay.
Sorry, n cube, n cube, n cube, 3. So it's 8/3. Yeah. So
8/3.
So it's substantial, but yeah.
Yes, I was thinking if the m equals n, but if m is big, then it would be more interesting.
Yeah.
It would be more interesting. Yes. Okay.
Do we have any other questions?
Stephen, by the way, I'm in the scientific board of Descartes.
Oh, I saw it. I saw it.
I never attended the meetings, but
oh no.
Too busy.
I understand. Yeah, I'm finishing now. I'm going to defend in 2 months.
Is Paco part of your thesis committee?
I think it's Elia Cuetos instead. Elia Cuetos. But yeah, I
Elias,
did. Yes, but Paco follows my work. But yeah, we invited Elias instead for the committee.
Okay.
But if you want to attend my thesis defense, I can send you a link.
Send me, yeah, sure.
Sure. Okay, thank you.
Tony Patera was my advisor.
Sorry?
Tony Patera was my advisor.
Oh, okay.
So I was his first student, and Ivan Madej, I know Ivan Madej since 86, 87 when he came to the MIT lab where I met him first.
Oh, interesting. I see. I've never met them, unfortunately, but maybe I should go to Jussieu in Sorbonne to see them one day. I will say
He's
hi
in
to them.
Sorbonne, yeah. Ivan
Yes.
Madej is in Sorbonne. I was in Sorbonne last summer, yeah.
But yes, okay, the small world. But yeah.
Thanks very much for the talk.
Thank you.
Yeah.
Thank you, everyone, and for the question as well.
Yeah, thank you so much. I think we don't have any more questions, so I think it's time to close the session. Thank you for your great talk, and thank you everybody for joining us today. Have a great weekend. Bye.
Thank you. Thanks for organizing as well.